So my name is Prasun Mahanti, and I'm going to talk about basically seasonal changes in the shadowed areas around the largest permanently shadowed regions. Um, we're not going to delve more into about why PSRs and how PSRs, but basically PSRs are the permanently shadowed regions which result because of the high latitude topographic lows due to the low obliquity of the moon. And they typically, they will exist at the bottom of these craters. And while the upper top parts of the crater rims, they will get the periods of direct illumination. They have unique thermal conditions, and quite a few of them, they actually have really low temperatures, which make them so interesting, right? So now, in this particular talk, I'm just going to focus on the three major PSRs. The reason I say that they're major is because they are the largest three PSRs as far as area is concerned, and they make up about 15% of the total South Pole, approximately South Pole PSR area. And the plot here, actually, you can see it's a descending area index of the South Pole PSRs, and these three are the ones that we are actually talking about. And why? Because they contain the largest amount of PSR area, even from the point of remote sensing point of view. They also represent the area that you're going to image more often, right? So that make them particularly interesting and useful. Now, here, what I'm going to show you is that what happens if we take the periods of solar illumination um, changing between the subsolar conditions from subsolar latitudes of like uh, high summer, peak summer in the South Pole, like minus 1.5, to the peak winter in the South Pole. And what we did here is that we took these different sets and we squished them down into one single image. And then from there, we actually outlined the shadowed area. So what we are going to see is the advancement of the shadow boundary. I'll play that once again. So that's what happens. So initially what happens during summer, it increases only slightly. But as you go towards the equinox, this is the blue boundary for the equinox. And then during the winter, they all just blend together and you get this huge blob of dark shadows, right? So, and this is kind of fairly intuitive, right? Because the PSRs are at the lower reaches. So as you're getting closer towards winter, the size of that shadow blob is actually increasing, right? Outwards, starting from the center of the PSR and just increasing outwards, right? So, but then what then makes them more interesting is that when we compare the areas, we see that over that period, the area actually increases about like 100 kilometers square. Now, again, there's a confusion here, is that what we would call as the PSR area. So we just track it here up to only like about 5% increase. When it starts blending, we just stop tracking it, right? And here is another example from a little bit different point of view. It's kind of more current. So what this is showing is the periods of the shadow around these three craters. Now, and on the right-hand side, you actually have a plot which shows the subsolar latitude. Now, up to this equinox position is where you can analyze for summer conditions. But after that, you would see that progressively you see more, the image on the left-hand side becomes darker and darker as it goes towards peak winter. And then again, as the winter passes, that I think happens around the end of August. So at that point, what happens, sorry, end of July. And then at that point, slowly again, you'll see that you have more and more illumination. What's important to kind of note here is that while it goes through all these different phases of illumination, because of the topography, there'll be spatial positions which will not receive illumination maybe pretty much the whole year, but maybe just one particular day or maybe a few hours of the day, right? And that's where it gets really more interesting. So this is a picture showing the number of days illuminated for the next year. Now, if you notice that, I mean, we already showed that the shadow boundaries advance and recede with time, right? The spatial transitions, as I was talking about, will not be smooth. So you might see, like, the light coming in here, and then you don't see, and then suddenly you'll see light here, right? And that's because of the topography. And sometimes it is actually very, very non-intuitive, okay, unless you actually follow the topography and look carefully. There can be regions around the PSR which will very briefly receive illumination. So the question that kind of comes naturally is that these are regions close to the PSR, but do they have temperatures like, like the PSR? And specifically, we're talking about the summer maximum, because they are kind of the cutoff for where we want to analyze these volatiles, right? So, and that's, I'll kind of skip this slide for now, because they just talk about the idea about the temperature and the volatile presence. But then in this slide, what we are showing that in this briefly illuminated range, I mean, the plots on the left and right side, you can see the correlation quite clearly, right? I mean, this is the temperature plot, and that's the number of days illuminated. But even here, so the 0 is just no illumination. So those are the PSRs. But even here, you actually have positions which have actually cold temperatures. And that's what we look into further, is that, again, on the left-hand side, you actually have temperatures, and this one has been filtered to less than 110 K because it's kind of a magic number right now, right? So, but then on the right-hand side, these are numbered and colored in the number of days that they are illuminated. Okay, now again, all this is again dependent on the scale-up simulation, the size of the pixel. These are all done at 240 meters per pixel, which is quite large, but that was easily correlatable with the diviner temperatures here, right? So you do see that even though that these are PSRs, but there are regions here which have illumination of the order of days, and still they are part of this less than 110K temperatures. So what we did is that then we we're trying to zoom in into all this different number of days of illumination. And the 0 is the PSRs. As you can see, for that, you can have temperatures ranging very close to like 40 to 110, because we kind of cropped it around 110 by the filtering process, right? But if we take these, which we are kind of right now calling them briefly illuminated, between 1 to 5 days, and we take the median temperature, summer max, then they happen to have values which are low. And they do have error bars on them, but then that's not.
2 minutes left.
So, and then this is another view of the same plot. As you can see, the PSR represent the majority when we take into account the number of 240 meter pixels. But then if you remove this guy, and then you can see all these baby things come up here, right? And you can see that there are quite a few of them. However, as you proceed towards the number of days, then the temperature also increases. They kind of follow in this direction, right? And that's what our previous plot kind of also showed, right? So again, going back, what we wanted to do and check this thing again with respect to subsolar latitude change. So we did that, and what we found is that up to 5% increase, up to 5% increase in the PSR area, when we look at areas around the PSR for these three major PSRs, we find that up to 2%, the temperatures are still below 110 K. And this is over a long period of time, right? And that kind of makes us interesting. And this is something that we're now trying to analyze even more. Just to kind of give a basic idea that how the imaging the briefly illuminated regions is really difficult, because first you have to have a proper instrument with a particular big field of view, and then the mission, you need to have the orbits in the right place, and then you do an extreme planning, and then you are ready for that, and then you just hope, and there are some X factors around that, right? Because what we found out that for the LROC NAC, we had in this area, which has like 1 day of illumination, we have just 9 observations in 12 plus years of the LROC NAC operation. So that kind of tells you that how difficult it is to image these regions at high spatial resolution. So in conclusion, the PSRs, there's a summer to winter transitions, and the total area of the PSR increases by about 100 kilometers square. The seasonally shaded regions of this frequency eventually merge during the winter. The temporal patterns of the PSR can influence the migration volatiles that you've heard of from other speakers earlier in this conference. And then the briefly illuminated regions, less than 2% temperatures are less than 110 K, and we are now checking that with respect to higher spatial scales. For a single year, the total illumination time with respect to the temperature less than 110 K can be up to 30 days, but we think that if we put a margin around 5 days, we should be able to get temperatures definitely within that range. And we have more analysis in progress with the already acquired LROC-NAC images, and we're looking forward to future images from both the LRO narrow angle camera and shadow cam over in the Danube mission at these locations. That's it. Thank you.
Thank you.